Hello everyone, so this is a video finishing up the last part of the chapter 17 thermodynamics notes, yay! And then, after this video, we'll move on to a little bit of practice and then some chapter 18 in that packet. So this is the last part of 17. So this is what your packet looks like. So this is like the student version that I provided for you on the agenda and I think on Google Classroom. So it started out with the heat of fusion solidification on the top of your first slide. And then it kind of looks like this. You got some popsicles in there. And then we stopped on this slide. And this is the last one I talked about, if you hopefully watched that video. So today we're going to start on the slide after this one. And I will tell you that it is a lot of math problems, so we'll get through it. So make sure you do watch this video because it will really help you during like those practice problems that I'm going to assign. But there's a ton of practice problems in this. And so if for whatever reason you don't get, it's okay if you don't understand how I did it. Just please email me or message me and say, hey, Ms. Murphy, I don't get how you did that problem on the video. Can you please like elaborate? And I will be happy to because there's one problem in here and it is a doozy. So if you don't understand it, please let me know. Okay. Okay. So I'll go to my version and leaving off right here. Okay. So we already talked about this. So now we're going to get into some practice problems, like I said. So the first practice problem, so this is the slide directly after that chart that we went over. And so this practice problem is asking us to find heat in kilojoules and how much heat in kilojoules is absorbed when 24.8 grams of water, liquid water at 100 degrees and that pressure is converted to steam at 100 degrees Celsius. So basically what this question is saying is how much heat is absorbed in the water when we make that transformation from liquid water to steam water at 100. And remember I told you on this graph that it happens, this is at 100 degrees. So because we know that this heat of vaporization and this transformation from liquid water to steam water is happening at 100 degrees Celsius, like I said, we can complete this problem. And this is a really simple problem. So all we have to do is, so first we're going to take what we're given, which is this 24.8 grams of water. We're actually going to disregard this other number that they threw in here. We don't need it for our purposes. So we're totally going to ignore that. Yay. And we're going to go do this 24.8 grams. And we're going to go ahead and set up a conversion. So one of those time sign fraction lines. And so I'm going to put it over 1. And then we need to get this 24.8 value into a term where we can use this conversion factor right here, the heat of vaporization, to calculate how much heat is absorbed. But we're not there right now yet because we're in grams and we need moles. But what's an easy way we can go from grams to moles? That's the molar mass. And so if we calculate the molar mass of water, we do 2 times 1.01, which is the mass of hydrogen, and then just plus 16. And I rounded oxygen's atomic mass. And so when we do that, we get 18.02 grams per mole. And so that is our atomic mass. And so we see we have grams on the top, so I'm going to put grams on the bottom. So I'm going to put 1802 grams for every 1 mole of water. And then now we can use this because we have moles. We have something we can convert to and from. So we're going to use moles, and remember, moles is on top here, so we're going to put moles on the bottom here. And then we know 1 mole of water is vaporized and absorbs 40.7 kilojoules of heat. And so because of these two conversions, it was pretty straightforward. So now we're going to calculate this out. I have my calculator right here. So 24.8. And I'm going to multiply across the top, across the bottom, because I know you guys are used to that. So I'm going to multiply across the top. So 24.8 times 1 times 40. And you get 1009.39. And if you multiply across the bottom, it's just 1 times 18.2. 18.02 times 1, and that's 18.02. So we end up dividing those. And so you end up with a final answer, 56.0 kilojoules. And that is our final answer. That was a really ugly. It's a really ugly block there. But that is our final answer. Let's see if we're correct. And we are. Yay. Okay. And then your notes does go through this step by step, but I wanted you to kind of see me do it. I think it helps see, fluid progression through the problem rather than stagnant typed out letters. Okay. So I'm actually going to come back to this problem. So this is slide number 68. Oh, it says right here. It says 68 right here. But I'm actually going to come back to slide 68 because remember when I said we have a doozy of a problem? This is that problem. So I'm going to come back to this. I'm going to do some more practice problems later on in this PowerPoint. And so once we do those, then I'll feel comfortable teaching you guys this, okay? Okay, so let's move on. Oh, those were the answers. All right. Okay, so here's another practice problem. I'm going to move my head here. Always in the way. Okay, so this practice problem asks, how many kilojoules of heat are absorbed when 0.46 grams of chloroethane vaporizes at the normal boiling point? The molar heat of vaporization of chloroethane is 26.4 kilojoules per mole. And so we're going to do the same thing we always do, which is start with our given. And so we are given this number right here, which is how much chloroethane we have. And so we're going to set up our problem with that as our beginning. And I want you guys to notice something. So when I did the first part of these notes last week, I didn't give you any formulas. All I gave you were these values. So I said, I told you what heat of vaporization, heat of solidification, heat of condensation, heat of fusion. I told you what they were, but I didn't tell you any formulas to use. And so that's because there are no formulas for this kind of stuff. When we're doing heat of vaporization, heat of fusion, heat of solidification, which one did I miss? I don't know. But when we're working with those heats of, there's no real equation to solve for those. You just use these conversion factors. And that's why, I've only been using conversion factors because, that's what you're supposed to do. Just kind of convert from one thing to another and use the heat ofs as your conversion factor. Okay, so that's why I haven't given you any formulas for this part of chapter 17 because there aren't any. So I didn't know if you noticed oh, we're not using formulas. How does she know what to do? Well, these are just conversions. Okay, so continue with our conversion. I'm going to go, I put my given, so 0.46 grams. And then I'm going to calculate my molar mass because we have grams and we can't use this yet because this is in kilojoules per mole and we have neither kilojoules nor moles. So we need to get one of the two, and the easiest thing to get from grams is moles using our molar mass. So I'm going to go ahead and calculate the molar mass from this. And so this is 12.01, that's for carbon, times 2 carbons, plus 5.05. That's for all, I clumped all of the hydrogens because for hydrogen it's 1.01 for each hydrogen, and then I just multiplied that by 5 in my head. And then chlorine is, geez, I think it's like 35. Oh, I think it's 32.51. Anyways, so when you add all those up, and there's only 1 chlorine, so I'm not multiplying by anything. When you add all those up, you get 60. No, this is 30. Why don't I just look instead of being lazy? Chlorine is 35.45. 35.45. So you end up getting 64.52, and that's grams per mole. And then, so I'm going to put my 64.52 on the bottom here. And then it's equal to 1 mole of this stuff on top. So now we have our conversion factors because we got rid of grams. Now we have moles, and so now we can use, now you see moles, yay. And so, didn't mean to make that an equal sign. This is a time sign. Now we can do our last part of the conversion, and so we put moles in the bottom. So we say for every 1 mole of chloroethane that is boiled, 26.4 kilojoules of heat are absorbed. So now we do that calculation. Again, I'm going to multiply across the top, across the bottom, and then divide them. So for the top, I'm getting, oh, yeah, that makes sense. I'm getting 12. So for the first part, we get 12.144. And then we're multiplying 64.52 times 1 times 1. So that's just 64.52. Then I'm going to divide those. So and this equals 0.188. And let's see if we're, oh, sorry, this is kilojoules. Let's see if we're right. 0.19 kilojoules is the answer. If I would have just rounded, that would have been perfect. Okay, let's continue. Okay, I'm going to move my head. So during the formation of a solution, heat is either released or absorbed. The delta H for solution, it's called the enthalpy change, caused by the dissolving of 1 mole of a substance, is the molar heat of solution. So basically the molar heat of solution is just when you dissolve 1 mole of something into the solvent. And so when you dissolve something into the solvent, it either requires heat or releases heat. So that's just another definition. So I'll give you guys a second to pause the video and then to write these definitions down, and then we'll continue. Okay, so you could have paused by now. Okay, and so this is actually something we experienced in class on one of the first days I was there, or the first day I was there, something like that. So this is saying when ammonium nitrate crystals and water mix inside the cold pack that the girl is using, heat is absorbed as the crystals dissolve, okay? So do you remember that first day in class? When we started chapter 17, it was like one of my first days, and I passed around that hot thing that was really hot, and I passed around the cold thing that was really cold. This is like the cold thing, okay? Remember, I crunched it up, I put some water in there, I mixed it around, and it felt cold to us, right? So that little packet, what it's doing is it's absorbing heat, and when something absorbs heat, when we feel that thing absorbing heat, it feels cold to us because the lack of heat in our hands, because it's going from our hands to the cold pack, that's why it feels cold, okay? And so this is just saying, you know, this is an example, a real life example of ammonium nitrate and water mixing and then creating an ice pack because it feels cold, because it's taking the heat from the skin and pulling it in to itself. So here is yet another problem. So let's do this together. So this is saying how much heat in kilojoules is released when 2.5 moles of NaOH is dissolved in water. First things first, we're going to write down what's given. And so we're given 2.5 moles. So I'm going to go ahead and write 2.5 moles over 1. And this is actually pretty nice for us because we're not given any mass. We don't have to convert from the mass to the moles. Moles are just given, so it's nice and easy for us. And so now we're going to use this just like the other, like the heats of. We're going to use this heat of solution, just like we did for the heat of vaporization, condensation, fusion, solidification, all those. We're going to use this the same way as a conversion factor. So we know that, you know, negative 445.1 kilojoules of heat are released when 1 mole of sodium hydroxide is dissolved in water. So we're going to use that as our conversion. So I'm going to say 1 mole. For every 1 mole of sodium hydroxide that is dissolved in water, 445.1 kilojoules of heat is released, which is why it's negative. And so that's a pretty easy calculation. We're just going to multiply across the top because the bottom is just 1. 2.5 times negative 445.1 kilojoules. So we get our answer to be negative 1112.75. I'm going to round it. So rounded, this is negative 1113. And then this is kilojoules that are released. So let's see if we're correct. Yay! So negative 1,113 kilojoules of energy is released. Okay? So that's an example of how you do a solution problem. This is a solution problem. And it walks you through it, but again, I feel it's better that you see me try it rather than it's just stagnant. Stagnant means like standstill. Numbers. Okay. Now we are on 76. So guess what we do? We start with our givens. So this is saying how many moles of NH4NO3 must be dissolved in water so that 88.0 kilojoules of heat is absorbed from the water. And so the past problems we started with the grams of stuff or the moles of stuff. This is when we're looking for heat and energy, but this is one where we're starting from heat of energy or amount of heat energy and going to moles. So it's a little flippy. So we're going to start out by looking at what's given, and this 88.0 kilojoules of heat absorbed is given. So we know this NH4NO3 absorbed 88.0 kilojoules, and we can use that to find how many moles of the stuff there were. So we're going to write 88.0 kilojoules over 1. Then we're going to do our conversion. We already have kilojoules, so we can automatically use this conversion right here, this like kilojoules per mole. So we're going to say this heat of solution. So I'm going to continue kilojoules in the bottom. So I'm going to say 25.7 kilojoules are absorbed. Sorry, I was looking for the word absorbed. So 25.7 kilojoules of heat is absorbed for every 1 mole of NH4NO3 that is dissolved in water. So now this is just another kind of easy problem. So if you want to, you can multiply across the top, and that'd be 88.0 times 1, and so you get 88.0 on top over here. And then if you wanted to multiply across the bottom, it'd be 1 times 25.7, and that'd just be 25.7 on the bottom. Or you can just divide them, because since you're multiplying by each, the top and the bottom, by 1, it's just going to be that number, right? So I'm going to do 88.0 divided by 25.7. And I get 3.42 moles. And that is our answer for this. So 3.42 moles. Let's see if we're correct. Oh my god, I wrote it in the exact place it popped up. That's kind of funny. But yes, so it's 3.42 moles exactly. So we're good. So now we have our end of chapter kind of section quiz. I'll kind of talk through these questions, because usually, in class I ask you guys oh, what do you guys think? But obviously I can't do that right now, which makes me sad, but whatever, I guess. So this question is saying the molar heat of condensation of a substance is the same in magnitude as its molar heat of. And so we talked about this in terms of the graph. So we said, I'm going to draw the graph really quick. So we said the graph is like this, and then at 0 degrees it melts from ice and goes to liquid, and then once it's fully in liquid form, it goes up again. It goes up again. Once it gets to 100 degrees, it starts to transition into a gaseous phase. Once it's in a gas, it goes like that again. Ooh, why did I do that? So we know that this is at 0, this is at 100. Oh god, that was bad. And this is degrees Celsius. And this is heat added. And so the reason I draw this graph to help answer this question is because it's easier to think about. So if we're condensing, okay, we're going from a gaseous state to a liquid state, okay? And remember that this is gas, this is liquid, and this is solid, okay? So remember, solid, when you're going from a solid to a liquid or liquid to a solid, you're going to use the heat of fusion or heat of solidification, because you're either breaking the fusion of those bonds in the ice to go to a liquid, or you're going from a liquid to a solid and solidifying it, making it into a solid. So it's not solidification, it's not fusion, because that's dealing with solids to liquids or liquids to solids. When we talk about, the boiling point, you are going from a gas to a liquid is called condensation, right? So think about when you have think about when you have a bottle of water in your car and it's really hot out. And the next time you go in your car, you're going to see little bubbles of condensation on it. That happens because, so as your car heats up the water inside the bottle, the water that's, heating up and evaporating has nowhere to go. So it's going to condense on the top of your bottle, and those are little droplets you see. And so the condensing is going from gas to a liquid. And so when we go to a gas from a liquid, we know we're in this stage, and we know it's going to be equal. That value is going to be equal if we go from liquid to a gas. So going from gas to liquid is the same, it should be the same magnitude of heat as going from a liquid to a gas, and we know going from a liquid to a gas is called vaporization. And so formation is just, that doesn't even make sense. So it is formation. Yay. Oh, yeah. This says the heat of condensation of ethanol is negative 43.5 kilojoules per mole. As ethanol condenses, the temperature of the surroundings So the first thing I think when looking at this problem is that we're given a numerical value. And that numerical value is negative 43.5 kilojoules per mole. And that's the heat of condensation. So it's the heat that's released. So I know when we're talking about heat of condensation, we're going from gas to a liquid. And when you go from a gas to a liquid, those are supposed to be colons, heat is released. And so if heat's released, that means the delta H is going to be negative. Remember that from, before we went on break, that lecture. So if delta H is negative, that means heat is going to be released into the atmosphere, into the surroundings. And so if heat is released to the surroundings, that means the temperature of the surroundings is gaining heat, and thus it will increase in temperature. There we go. Okay, so we have a little practice calculation problem. So calculate the amount of heat absorbed to liquefy 15.0 grams of methanol at its melting point. The molar heat of fusion for methanol is 3.16. And so first we're going to take what we're given, as always. So we're given 15.0 grams. And we need to go from grams, like we have in the past couple problems, we need to go from grams to moles, because we need those moles to use this. We can't use grams because we don't have anything to convert with grams in this heat of fusion. So we need to get moles. And so the only way we can do that is if we calculate the molar mass. And so the molar mass of this I will calculate up here. So C is 12.01 plus, there's 4 H's, so these 3 H's plus this one is 4. And so 4 and 1.01 times 4 is 0. Plus the 1 O, which is 16.00, and there's only one of those. And so if you add those all together, you get 32.05 grams. And so if we use this molar mass, this is grams per mole. If we use that molar mass and say 32.05 grams on the bottom, because we have grams here, grams top, bottom, and what per 1 mole on top. And now we can use this conversion factor. And so we say 1 mole of methanol liquefied absorbs 3.16 kilojoules. So if we multiply across the top, you will get 15 times 3.16. That's 47.4. And if we multiply across the bottom, it's just 1 times 32 times 1, which is just 32.05. We can divide those. So 32. And I get 1.4789. And so rounded, that is 1.48 kilojoules. Do I see that as an answer? I do. That's this one. Let's see if we're right. We are right. So this is good. Okay, last practice problem for this one. So this is saying how much heat in kilojoules is released when 50 grams of NH4NO3, which they give us is 0.510 moles, are dissolved in water. And they give you the delta H of solution. So this should be delta H. So it's nice of them to give us moles, because now we don't even need to look at this, because we're like, oh, okay, they already gave us the moles. We don't even need this anymore. So we're going to look at the moles we're given, and so that's 0.51 moles of NH4NO3. So I'm going to put that given over 1, and we don't need to convert to molar mass because we're given these nice moles here. And so I'm just going to go right ahead and use this. So say for every 1 mole of NH4NO3, 25.7 kilojoules are released. And so if we multiply that out, we get 13.107, or rounded, that is 13.1, and that is in kilojoules. Do we see that on here? We do. See if we're right? We are right. Okay, so the last slide before I do that big giant calculation is this, talking about Hess's law. And basically what Hess's law tells you is that if you have 2 or more thermochemical equations, you can add those heats of reaction to give you the final heat of reaction, okay? And so it's like an easier way to determine the heat of reaction than, doing all the equations individually if you know that they're equal, okay? Unfortunately, there's no examples in this slide, but now we can go back to slide 68, so I can do that crazy long problem, which is this one. Now we'll start this problem. Okay, I moved my face over here so I wouldn't be in the way. Okay, so this question says 355 grams of ice at negative 23.1 degrees Celsius is heated to 115.1 degrees Celsius. How much energy is absorbed for this transition? So you might think to yourself, the initial approach to this problem is just to go and put, go and solve for Q and put your 355 into M. You have your delta C down here into C, and your delta T would just be 115 minus negative 23. But that is not correct, and this is why. When you're going from ice to liquid, remember you have that heat of fusion that you need to deal with, and that in itself is that's a whole separate energy that's required to take the water from ice to a liquid. Then once we're in the liquid, that will just heat up like normal. But then once we're in that, at that 100 degrees Celsius, that's where we're going to start to boil, right? And then we have to deal with heat of vaporization. And we have to calculate that quantity because that's completely different from just raising the temperature. Because remember, that graph looks like this. It looks like this, and then you go flat line, then up, and then flat line again, then up some more. So remember, you have those flat lines, and because of those flat lines, the temperature is not increasing there. So we can't really use delta T at those points because temperature is not increasing or decreasing. It's the same here, right? And so that's when we have to do those conversions to find how much heat is released, or in our case, absorbed, to see how much energy is being used, okay? So I'll walk you through it in 5 steps because, we're going from ice, and then the heat of fusion, then liquid, and then heat of vaporization, and then we're in gas. So it's going to be 5 steps, and that's why I said it's long. So step 1 is to convert. So we know at 0 degrees Celsius is when that phase change is going to occur, and so that's when we're going to be flatlined. So up until 0 degrees Celsius, we can have that increase in temperature. So we can do our Q. And so we have 355 is our mass. Our C for ice is this. So we have our 2.05. And then our delta T is going to be 23.1 1 degrees Celsius. And so remember, when we get to 0, that's when our phase transformation is going to happen. And that's why I only went from negative 23 degrees to 0. And that difference in temperature is just 23 degrees. So I'm going to do 355 times 2.05. And this is point. Stop it. Ooh, no. This is point. Times 23.1. And you get this big number, which is 16,8111. But they want it, and this is joules, but they want it in kilojoules. See all these kilojoules here? They want it in kilojoules. So just to convert joules to kilojoules, you just divide this number by 1,000. And if you need me to clarify that, you can message me and say that doesn't make any sense, Miss Murphy, and I will clarify on why you divide by 1,000 to convert from joules to kilojoules, okay? This is the answer for our first step. So to go from negative 23 degrees to 0 degrees, the ice absorbs 16.8 kilojoules of energy. Step 2, because we're now at 0 degrees and we're flatlined, and we need to go do our phase transformation. This is where we're going to do one of those conversion factor looking ones. So we're going to start with and so like we always do, I'm going to use the molar mass as our conversion factor from grams to moles. And so we know that since we're working with ice, and then ice is just water. And so we know from an earlier problem that ice's molar mass is 18.02 grams per mole. And so I'm going to put 1802 at the bottom, grams. And then we put 1 mole on top. And so now we're into moles. So now we can use this, this molar heat of fusion. Because molar heat of fusion, remember, is when you're going from solid ice to liquid water. So I'm going to say for every 1 mole, 6.02. Kilojoules is used. So if we calculate that, we get 118.6 kilojoules. And this is already in kilojoules because we have kilojoules here. And then on to step 3. Now that we're past the phase change, we're increasing again. So now we passed this solid to liquid phase change. We're completely a liquid now. And we are just going from 0 degrees to 100 degrees because we know 100 is the next phase change, okay? So we're going to do another one of these Qs. So we're going to say Q is equal to 355. And then this time we're going to use the specific heat for liquid water, and that's 4.184 joules per grams degrees Celsius. And then our delta T is going to be 100 degrees because that's what we're going to our next phase change. Our next phase change is at 100 degrees. So we're going from 0 to 100, and 100 minus 0 is just 100. So if we calculate that, we get this really huge number. 148,532. Again, this is in joules because this because the value of C is in joules per grams degrees Celsius. We want it in kilojoules so that units are the same. So we're going to go ahead and divide that by 1,000 to convert from joules to kilojoules. And so we end up getting 148.5 kilojoules for this. Now we're at the next phase change because we're at 100 degrees now. So we're going to say part 4 is another one of these conversion problems. So again, we're going to say 355 grams over 1 times, and we already have this right here. We already have our molar mass set up, so we can already just go and jump right ahead and do that because we already have our molar mass calculated. 2.02 grams for 1 mole of water, times sign, fraction line, and we have our molar heat of vaporization because right now we're going from a liquid to a gaseous state. So we're going to use our molar heat of vaporization here, and that is 40.7 kilojoules per mole. So for every 1 mole to go from liquid to gas, it takes 40.7 kilojoules. So now if we multiply it across the bottom, across the top, and then divide, see what we get. We get 801.8 kilojoules. Remember, this one is in kilojoules because we have this here. And so now we're on to our last step. This is going to be step 5. And so this is when, we're completely steam now, and we're just going from 100 degrees to this final temperature of 115. Okay? So we're going to do another one of our Q's. See how it's in a pattern? It's like Q, conversion, Q, conversion, Q, conversion. So for every phase change, you have to do the conversion kind of thing because you're using your heats of. When I say heats of, I mean like you're using your heats of. And that's when you're going to do the conversion. And then whenever you're using your specific heat, you're going to use Q, the Q equation. So I'm going to say, no, don't do that. That's kind of interesting. Okay, so we have our 355 grams, and then our delta C for steam is this 2.01, and then we have our delta T, which is 115.1 minus 100, and that just equals 15.1. So I'm going to put 15.1 for this, and now we can just divide it out, get our final answer here. 355, 2.01, 15.1, and that is 10,774. But that's joules, and remember we want kilojoules, so I'm going to divide this by 1,000 to get joules to kilojoules. And so when we, didn't mean to do that. Divide by 1,000, and we get 10.77 kilojoules. Now we can calculate the total energy used throughout this to go from solid ice to steam of 115.1 degrees Celsius. So we just are going to add all of these up. So we're going to add this up. So the 60.8 plus 118.6 plus 148. 8.5 plus 801.8 10.8 plus 10.77. And so we get our total to be, and I'm rounding here. Oh, don't do that. 1,997, and then this is kilojoules, and this is our total. Okay, so we can check ourselves. Let's see if we're right on this really long problem. So again, I'm going to move my face here. So the first step should be 16.8. We got 16.8. If you can't see, we did. Step 2, we got 118. We did get 118. Step 3, we got 149. We got 148.5. So same thing. For 4, we got 180. We got 801.8, which is, super similar to 802. And then for 5, we got 10.8 here, and then I got 10.77 down here. So if I would have just rounded up, it would have been 10.8. And then the total is 1,097, and we got that exactly. So we did this right. I know that was a really long, kind of confusing problem. That's why I braced you for it and did everything else and then came back to it, because I know that this is kind of a crazy long problem. I don't see myself giving you a problem like this on a test, maybe on like a practice sheet, just to see if you, watched this video and picked up any of the how-tos for this problem. So maybe I would do it on a practice problem, but I would never put this on a test. But I mean, it is good to know how you see the difference from just heating something up versus phase changing it. Okay.